the next problem now, we have a 10 loop turn of wire. It's lying in a horizontal plane parallel to a uniform horizontal magnetic field. So let's see, we'll call horizontal X, so the plane of the loop is in X, Z, and the vertical will be Y. So our loop now is in the XZ plane. The current is 2 amps. Notice it doesn't show the direction of current. That's something to keep in mind. The loop is free to rotate about a non-magnetic axle through the center. So this axle then is the pivot of rotation. A 50-gram mass hangs from one edge of the loop. What magnetic field strength will stop the loop from rotating? So this is going to be a problem where we don't want it to rotate, so we know we're going to need the net torque to be 0. This exerts a torque because it pulls down on this side. If there's a current flowing through here, there's going to be a magnetic moment, and we know that loops in magnetic fields experience torques. So our torques will be due to this hanging mass, and the torque will be due to the magnetic field, and those torques are going to have to be equal and opposite. So let's make a list of the things that we know right off the bat. The number of loops is 10, so N equals 10. The current flowing through the loop is 2 amps. The mass hanging off the loop is 50 grams, 0.5 kilograms. And this side length is going to be 5 centimeters. So we know that the net torque is going to be 0. So let's write that expression down. So the sum of the torques acting on that loop, where torque is a vector, is equal to 0, which means that the torque due to the hanging mass, I suppose you could also call it the torque due to gravity, doesn't really matter, plus the torque due to the magnetic field is equal to 0. So these torques will have to have opposite directions. They'll have to provide rotation in opposite directions, opposite senses, and they'll have to have equal magnitudes. So the torque due to the hanging mass will have the same magnitude as the torque due to the magnetic field. Okay, let's write expressions for both of those guys and see where that takes us. The torque due to the hanging mass, the magnitude of the torque due to the hanging mass, let's use our expression for torque, that's R cross F, will be R cross F. So then that's going to be the magnitude of R times the magnitude of F times the sine of the angle between R and F. R is the distance from the pivot, which is the axle that goes down through the center, from the pivot to the point where the force is applied. So let's see if we can get that on the diagram halfway neat. So there's R, and here's our force. So the mass pulls down on a loop with a force equal to its weight. So if we look here, R is the distance from the axle to the line. That R is going to be half the width of that loop, 2.5 centimeters. So the magnitude of R, let's write this in meters, 0.025 meters, times the magnitude of the force, Fg is m times g. So it's going to be the mass, 0.050 kilograms, times g, 9.81 meters per second squared. The angle between R and F, this is in the x plane, this is in the y plane, that makes that angle 90 degrees. And sine of 90 degrees is just 1. So if you wish, you can do that on your calculator. You should get an answer of 0.0123 newtons times meters. So there's the size of the torque due to that hanging weight. Now what we know is that the size of the torque due to the magnetic field is also going to have that magnitude so that they can cancel. So let's write down what the torque due to the magnetic field is. Torque due to the magnetic field is mu cross B. So the magnitude of the torque is the magnitude of mu cross B. The magnitude of mu times the magnitude of B times the sine of the angle between them. Now this one's interesting. So the magnitude of mu is n, the number of turns, times I, times the area of the loop, times B. Magnitude of B is just B. The angle here, well, I guess it has to be 90 either way. We don't know the sensation of the current. Is it coming around this way? If it comes this way, the area vector is up, or does the current come this way? If it does, the area vector is down. But regardless of whether it's up or it's down, that angle will be 90 degrees. So our N here is 10. Our current I is 2 amps. Area is length times width. And then our magnetic field is what we're trying to find out. We'll just leave that as B. So then if you multiply all these numbers together, you should get 0.1 with units of amps times meters squared times B. So now we know those two guys have to be equal. Let's set them equal. I wonder, can I just do that up here? And try and squeeze that in up here. 0.0123 Newton meters equals 0.10 amp meters squared times B gives us B is 0.0123 divided by 0.1, 0.123 Teslas. And we already know the direction. It's given to be in the x direction. Now let's ask the question that it didn't ask, but maybe we should think about anyway. What direction does the current have to flow? Because we have two options. It can come up this way and around the loop here, or it can come around the loop this way. So I think that's a good question to ask and see, can we figure it out? So what is the direction of I? That's like a bonus question. And it actually really does matter. If I is not in the right direction, your torque won't be in the right direction. So if we look at our loop, if we want the net torque to be 0, there's a force pulling down on this side. We're going to need a force pulling up on this side. Okay, so the only way to get the net torque to be 0 would be to balance all the forces so it doesn't rotate. To balance this downward force, you've got to have an upward force here. Okay, so we know that FB equals IL cross B, and we know that we use our right-hand rule for this. We know the direction of FB, we know the direction of B, so we can work backwards to figure out the direction of I. So in our right-hand rule, our resultant is our middle finger. That has to point up in the y direction. B is, I'm just going to try and line up with my loop here. So our magnetic force comes up, B comes to the right, so our index finger is I. So B cross I gives the force. So the current I must be going up in the loop this way to give an upward force on this guy. So I has to flow this way to give the right direction of the force. So the direction of current flow I don't know which words to use to describe that, so I'm just going to say as shown. If the current flowed the other way, that magnetic force would be down, and you couldn't get a balancing of the torques. Okay, we'll do one more example, and then we'll be finished up with this section.